Hi, I'm Bill Kuszmaul. This is joint work with Shyam Narayanan, and this talk is titled Stochastic and Worst-Case Generalized Sorting Revisited. In the generalized sorting problem, you're given a graph, and you want to sort the vertices in that graph. And you can compare pairs of vertices, but the catch is that you can only compare two vertices if they form an edge in your graph. Now, a priori, it might not be possible to fully sort the vertices in this way. But the other thing that you're guaranteed is that the true order of the vertices appears as a Hamiltonian path in your graph. So this means that at the very least, if you were just to query all of the edges in your graph, you'd be able to deduce what the true ordering of the vertices is. That's the generalized sorting problem. And the generalized sorting problem comes in two flavors. So the first is worst-case generalized sorting. Here, your edges could be arbitrary. And the second is stochastic generalized sorting. This means that each pair of vertices is included as an edge independently with some probability p. And then, of course, you also have a planted Hamiltonian path representing the true ordering. But besides that, your edges are random. That's the two flavors of the generalized sorting problem. One of the things that's interesting about the generalized sorting problem is that, on one hand, it's one of the most natural generalizations of classical sorting, but on the other hand, it's not obvious a priori that you can do anything better than the trivial thing of just querying all of your up to n squared edges. And so that's why it was a kind of big breakthrough when, in 2011, Huang, Kanan, and Hakana figured out that actually you can solve worst-case generalized sorting in soft O of n to the 1.5 comparisons. That's a lot better than n squared. And even better, in the stochastic case, they were able to improve this to soft O of n to the 1.4. And here what's actually going on is the number of comparisons is a min of two terms. So the first term is for an algorithm that does well in the sparser case, where your graph is relatively sparse. Here, n is the number of vertices and m is the expected number of edges. And the second term is an algorithm that does well in the denser case. And if you take the min of these two things, you always get something that's at most soft O of n to the 1.4. So this spawned a whole bunch of interest in the topic. There's a whole bunch of interesting follow-up work. For example, one question that was considered is, what happens if your graph is really dense? It contains all but, say, L edges. Then can you get a good number of comparisons in terms of L? Or what happens if you have some prior beliefs about how different pairs of vertices should compare? You have predictions, and you want to bound your number of comparisons in terms of the number of predictions that are wrong. So a whole bunch of interesting follow-up work. But nonetheless, for the kind of vanilla version of these two problems, these initial 2011 bounds have remained unimproved until now. And so that's the goal of this paper. Can we improve these bounds? We have two main results. Our first result is for the worst-case generalized sorting. Here we give an algorithm that takes time soft O of root nm. And so you'll notice that actually, in the case where your graph is very dense, it contains order n squared edges, this actually isn't an improvement on the previous state of the art. But as your graph gets sparser, it is an improvement. And in particular, as your graph goes towards having constant out degree, the expected number of comparisons tends towards soft O of linear. You'll notice also that the square root of nm term is one we've already seen. So it shows up in the sparse case for the previous stochastic algorithm, which raises the question of whether for stochastic sorting we can actually do any better than for worst-case sorting. And our second result, which is actually our main technical result, shows that we can actually do really well for the stochastic case. It turns out we can solve stochastic generalized sorting where the expected number of comparisons is order n log m over n. So this is always at most order n log n. But actually, in the case where your graph is sparse, for example, if your average out degree is polylogarithmic, then this would actually become order n log n. So this is actually kind of flipping the story in some way. Kind of in the past, we've been thinking of the question being, how much harder is the generalized sorting version of the problem than classical sorting. And what this result is saying is actually no, stochastic generalized sorting can actually be performed in fewer comparisons than classical sorting. And the intuition here is that, especially when your graph is sparse, you're actually getting information out of the fact that you know that the true ordering appears as a Hamiltonian path. And that's what makes it, at least information theoretically, possible for us to do better than in the classical model. So let's dive into the stochastic generalized sorting result in a bit more detail. We actually proved two theorems. So the first is the one we've already seen, the upper bound, that we can do n log m over n comparisons. Another way to write that is n log pn, where p is the probability that a given pair of vertices is an edge. And then the second result is a matching lower bound. We show that actually our upper bound is tight for almost all values of p, with the exception of when p is really small, so when your average out degree is log n or smaller. And that case actually still represents an interesting open question, because that's the regime where if your graph is random, you don't actually expect there to be a Hamiltonian path by pure luck. And so the fact that there is a Hamiltonian path actually reveals information about the true ordering even before you've done any queries. And so it might be possible to actually improve the upper bound in that case. Okay, so for the rest of this talk, what I want to do is I want to dive into our algorithm for this case. How do we actually get order n log m over n? And for concreteness, I'm going to set p, the edge sampling probability, to be 1 over root n for the rest of this talk. So each pair of vertices is an edge with probability 1 over root n. Okay, the basic structure of our algorithm is that at any given moment we're going to maintain what I'm going to call a funnel. And the top level of this funnel is a set L1 consisting of all the remaining vertices. And then the subsequent levels have the property that each subsequent level is a subset of the previous level. The goal is that it should contain about half as many vertices as the previous level. And the idea is that we want to filter out large elements while letting smaller elements propagate down to smaller and smaller levels. And the reason that's useful is that this means that the minimum, the true smallest remaining element, is going to make it all the way down to the smallest level, and that'll make it so that we can efficiently figure out which element is smallest. Okay, so we'll go into more detail about the structure of this funnel in a second, but first let me describe the high-level structure of our algorithm. The high-level structure is that first we build this funnel, then we use this funnel to find the smallest vertex in our graph and remove it. And now we have the option of rebuilding our funnel from scratch. But that wouldn't be very efficient, so what we do instead is we figure out how to kind of incrementally update our funnel to account for the fact that we've just removed a vertex. And now we can rinse and repeat. We find the new smallest vertex, we remove it, we update our funnel, and so on and so forth. Now let's dive into each of these pieces of the algorithm in a little bit more detail, and maybe I can give you some intuition for what's going on. So the first question is, how do we build the funnel? And for this, what we really need to be able to do is to answer the question, if we have some vertex x in some level li minus 1, we have to decide whether we're going to promote x to also be in level li. And we can answer that question as follows. First, we consider some big constant c, and we look at level li minus c. That's the level that's c levels larger than the one that x is currently in. Then what we do is we randomly sample a constant number of edges in expectation from our vertex x to random vertices in level li minus c. Here's where we're using the fact that we have access to random edges. And then finally, we query each of those edges. So we compare x to each of the vertices. Here we're calling them y, z, and w. And the rule is that if x is smaller than all of those vertices, then x is promoted to get to be in level Li. On the other hand, if x is larger than at least one of those vertices, then we say x is blocked from being promoted, and it's blocked by whichever vertex is larger than it. And so the idea here is that if x is really small, it has a good chance of being promoted, and if it's really large, it has a good chance of not being promoted. One thing that's interesting here, and kind of subtle, is that it's tempting to do this process by just comparing x to other vertices in level Li-1. But it ends up being important that instead we actually compare x to vertices in a level that's c levels higher for some large constant c, because it turns out this actually makes our levels kind of evolve in a slightly more predictable way that ends up being important for the analysis. So by comparing to a level that's higher up, and then comparing to a large constant number of vertices in that level, we end up making it so that our levels behave better as we construct smaller and smaller levels. Now that we've built the funnel, the next question is, how do we actually find the smallest vertex in our graph? And here we immediately encounter an obstacle, which is that our smallest level, let's call it L sub b, actually doesn't just contain a single vertex. Instead, it turns out it actually contains, in our case, about root n vertices. So why is that? Well, there comes a point where our level is so small that when we try to find edges from a vertex x in our level to a level c levels higher, we actually can't find any edges. We don't have enough edges to do that. So there comes a point where we can't continue to make smaller and smaller levels. And in our setting, where we selected p, our edge sampling probability, to be 1 over root n, it turns out this means that we bottom out at a level of size roughly root n. So how do we figure out which of these root n vertices is actually the smallest? Well, here we use a trick. We look at the vertex v that we most recently removed. So the vertex that a moment ago was the minimum, but we removed it. And we take advantage of the fact that the true ordering of the vertices has to appear as a path in our graph. So that means the new min, the vertex we're currently looking for, actually has to be incident to vertex v. And now we're benefiting from the fact that vertices have possibly a relatively low out degree. So in our case, an expected out degree of root n. Because this means that actually we eliminate almost all of the candidates in our level LB, and it turns out we're left in expectation with only a constant number of remaining candidates for who the smallest vertex is. Okay, but we've still got a problem. So these blue vertices, the ones we haven't grayed out, we still don't know which of them is the min. And here we do something that's actually potentially very expensive. We go through each of the levels above the smallest one. We start with the smallest of these, L sub b minus 1, then we go through LB minus 2, and so on. And for each of these levels, what we do is we actually query all of the edges that go from that level to our candidate vertices. And we use the outcomes of those queries to try to eliminate candidates, to try to show that actually some candidate isn't the minimum because we found a vertex that's smaller than it. And so this is potentially very costly, but what it lets us do is eventually we eliminate all but one candidate, and now we've identified the true min. And this is one of the pieces of the algorithm that ends up being especially interesting to analyze, because it turns out you actually can show that the expected number of comparisons that you do here is only logarithmic, and that's important to showing that our algorithm is efficient. Okay, so now we've found the smallest vertex, and we've removed it, but we need to update the structure of our funnel to account for the fact that we've just removed that vertex. How do we do that? So let's say that the vertex we just removed is called V. And what we're going to do is, usually when we remove a vertex, we're just going to do kind of a temporary fix to try to make our funnel be kind of updated. What we're going to do is that if there were any vertices x in any levels, if there were any vertices x that were previously blocked by V from being promoted, now we're going to give that vertex the opportunity to be promoted. So there's going to be some vertices in some levels where V previously blocked that vertex, and now we let that vertex go to potentially smaller levels. So that's our temporary fix. And then the other thing we do is that every once in a while, we actually take a level and rebuild it entirely from scratch. And by doing the temporary fix, that makes it so we don't have to rebuild the levels too often, and this lets us maintain the levels efficiently over time. And one thing that's cool here is that because of this way in which we're doing these temporary fixes, the structure of our levels at any given moment is kind of this interesting, complicated function of the order and times at which vertices have been removed. And so that's one of the things that makes the algorithm kind of subtle to analyze. Okay, so now we actually have all the components of our algorithm. What we do is first we build the funnel, then we find the smallest vertex and remove it, then we update the funnel. So usually this just means we do a temporary fix, but occasionally this means we rebuild entire levels, and then we rinse and repeat. We find the smallest vertex and remove it, update the funnel, and so on. That's the structure of our algorithm for stochastic generalized sorting. Okay, so I want to conclude the talk by just emphasizing two open problems. The first open problem is, you'll remember that for stochastic generalized sorting, our bounds are actually tight in all but one regime, the regime where your graph is really sparse. The regime where your graph is so sparse that you don't expect a Hamiltonian path to occur by pure chance. And this is the regime where it's kind of an interesting question whether maybe we can somehow actually improve our upper bound and get an even better bound. Maybe even, for example, a linear number of comparisons. Or alternatively, can you get a better lower bound? The second open problem, of course, is can we do even better for worst-case generalized sorting? In particular, can we, in the case where your graph is relatively dense, it contains order n squared edges, can we do something that's better than n to the 1.5? Or alternatively, can we prove any non-trivial lower bounds, showing that, for example, worst-case generalized sorting is genuinely harder than classical sorting? So those are two open problems that I'd be really interested to see progress on, and that concludes the talk.